Hello, everyone, and welcome back to another episode of From Alchemy to Atoms. I am your host, David Johnson. This is the fourth episode in the series, and this is the second of a two-part episode about the Hellenistic period. So in episode 3, our last episode, I introduced you to Alexander the Great. We talked about what the Hellenistic Age was, and then I introduced you to two of the great thinkers from that period, Euclid and Archimedes, both of whom made significant contributions to the field of mathematics. Today we're going to continue that story, and I'll introduce you to three more thinkers from the Hellenistic period, all of whom will make significant contributions to our understanding of mathematics and science. Before I do that, I do want to give a small apology. I don't really have a corrections corner for today, but I do want to apologize for the fact that this episode is a few days late. I had a family vacation planned for last week, and it didn't really strike me as being problematic until we were driving home, and I was like, oh, pretty sure I was supposed to have an episode out today, so I apologize for being a few days late, but we'll get back on track after this episode. So today's episode is going to continue our conversation about the Hellenistic period. And like I said, I'm going to introduce you to three different Greek thinkers that lived during this period and made significant contributions to our understanding of mathematics and science as a whole. So the first person I want to introduce you to is Eratosthenes of Cyrene. So Cyrene, also pronounced Kyrene, or if you lived in the time of Eratosthenes, you may have actually pronounced it Kyrene, is actually modern-day Libya. It's part of the country of modern-day Libya, I should say, in northern Africa. So Eratosthenes of Cyrene, that's how I'm going to pronounce it. I'm labeling as the Great Librarian, kind of continuing in that trend of giving these guys names that will help you remember their contributions moving forward. So we know a lot more about Eratosthenes' life than we do the other two men that we met in the last episode. So like I said, we don't know much about Euclid's personal life. We don't know a ton about Archimedes, but we do know a lot about Eratosthenes. So we know Eratosthenes was born in the year 276 BC in Cyrene. As I mentioned, this is part of modern-day Libya, and this region of the world was actually captured by Alexander in 332 BC. And after Alexander's death, Cyrene became part of the Ptolemaic kingdom, which was one of the Hellenistic kingdoms that flourished under Greek influence. So even though Eratosthenes was born in Cyrene, at this point, that was a very Greek part of the world. It had been for almost 50 years at that point. So he would have come up with a very Greek sort of grounding and understanding of the world. Now, the Ptolemaic kingdom stretched over much of northern Africa. This was led by several pharaohs, so it's called the Ptolemaic kingdom. It began with Ptolemy I, and then ended actually with Cleopatra. So we'll actually talk about that towards the end of the episode. So if you're thinking of Cleopatra, Mark Antony, we're getting there. We're actually closing in. We're a couple hundred years away from her being relevant to the story. Now, Eratosthenes spent his early years in Cyrene, but then traveled to Athens in his young adulthood because he wanted to study under some of the most influential scholars of his time. And like a good Greek person, one of the first things he was interested in was learning more about philosophy. So we'll talk about Stoicism a little bit later, but he studied Stoicism under the founder of this philosophy, a man named Zeno of Citium, and another important Stoic philosopher called Aristo of Chios. So he gets this grounding in Stoicism, but interestingly, his first work would actually be inspired by the work of Plato. So he learned about Platonic thought from the head of Plato's academy at the time, whose name was Arcesilaus of Pitane. And the book that he writes, based on the knowledge he gains from Arcesilaus, is called Platonicos. And here, he's really focusing on the mathematical underpinnings of Platonic philosophy. And I'm going to remind you again, one of the things I told you about Plato, one of his major influences on thought moving forward is looking at more of a mathematical understanding of the universe around us. So this whole book written by Eratosthenes is looking at how does Plato's thinking utilize mathematics to help us understand the world around us. While he was in Athens, he also wrote and published several poems about Greek mythology. He was also interested and wrote books chronicling historic events. So, for example, he wrote books that included the chronology of the kings, the people who ruled over Greece, the Olympic Games. So we're probably all familiar with the modern day Olympics. Most of us know that that started back in ancient Greece. This was something that happened on a cyclical timetable, and he began chronicling all the winners of the Olympic Games. And because of this, he's actually known as the father of scientific chronology. What I mean by that is he began using historical records in an effort to calculate the specific time in history when specific things occurred. So instead of being like, this happened a long time ago or several years ago, he was like, no, can we put an actual, like, this happened in this year? And by taking historical documents, comparing historical references to when certain people lived, he was able to begin forming essentially a chronology of the history of certain aspects of Greek life, which is really interesting and useful to us, 2,500 years later or 2,000 years later, as we try to understand when certain things happened. So we get a lot of that from the work of scientific chronologists like Eratosthenes. Now, his work in poetry, his other writings caught the attention of King Ptolemy III. So this was the pharaoh of the Ptolemaic Empire at this point in time, or the Ptolemaic kingdom that was ruling over much of Africa. He recruits Eratosthenes to Alexandria. Once again, we're back in that Egyptian city of Alexandria. And at the age of 30, Eratosthenes moves from Athens, comes to Alexandria, and agrees to be one of the librarians in the Great Library of Alexandria. Within 5 years, by the age of 35, he would actually be the chief librarian. So in this role, he actually became friends with Archimedes. So if you recall, in our last episode, we talked about Archimedes writing this treatise called The Method of Mechanical Theorems, where he devised a way of sort of physically modeling scientific mathematical problems and solving them mechanically. And then remember, he was also kind of like, but this isn't good enough, and I need to find a way to prove this, mathematically. And he kind of reverse engineered his equations from that. So remember, that whole thing was a letter that Archimedes had written to Eratosthenes. So you have two of the great minds of the Hellenistic period talking with each other. There's just this ongoing dialogue between these two. And Eratosthenes would have this with several other people, but relevant to this story, we'll talk about his relationship with Archimedes. Now, during his reign as the head librarian, he undertook a massive expansion of the library's holdings. So he gets a royal decree passed that basically says all books in existence need to be surrendered to the library for duplication. So remember, there's no copying apparatus. There's no copiers. There's no photocopying. There's no Xeroxing. There's no dittoing. There's no scanning. There's nothing, right? There isn't even a printing press. So if you want to make a copy of a book, you need to get the book and then have somebody actually rewrite everything that's in that. And if there are illustrations, do that and that kind of stuff. So what ends up happening is all of these books that are available come to the Great Library, and in due time, they take these books and they copy them so that there is at least one copy of that text in the Great Library. Then you could have your book back. It was said that the duplication process was of such high quality that it was often impossible for the owner to determine which book was the original that they had submitted and which was the duplicate. And this is a pretty big thing because again, you don't have a copy machine. So you're really relying on the copy machine is another person. So the fact that they were able to produce such high quality copies is something that's very impressive and it is worthy of note. Now, Eratosthenes, in addition to just sort of really beefing up the Great Library, and remember, as I talked about in the last episode, this is kind of like the Google of the ancient world. You don't have an internet. So if you want to find information, you've got to find it somewhere. And the Great Library becomes this great hub of all of the world's knowledge, in part because of the work of Eratosthenes. But Eratosthenes also had his own work. He had stuff that he was interested in, and he made several important contributions to our understanding of the world. So I'm going to break these down as I've done in previous episodes, kind of by each contribution and talk about it and why it's important. So the first thing I'm going to throw out there is that Eratosthenes measured the circumference of the earth. Would it surprise you if I told you that a man living in Egypt in the 3rd century BC properly calculated the circumference of the earth to an accuracy of between 1% and 3%? If you are shocked, then you are me. Because when I read about this, it surprised the hell out of me. And the way he does it is both simple and elegant. He did it by measuring shadows. So here's how he does this. Eratosthenes erected 2 poles. They're called gnomon, Gnomon, in case you ever get into a spelling bee or you need a word for Scrabble. He put one of these in Alexandria and another in the city of Syene, not Cyrene, Syene. It's all in modern times, it's actually known as Aswan. Okay. So he puts one in Alexandria and one in Syene. And then he had the exact distance between these poles measured by professional bematists. These are step measurers. They are professionals who measure distance in paces. They know how big their steps are. They literally walk from one point to another and measure things in paces. And then he waits for the summer solstice. And what he does is at midday on the solstice, he asks that the angle that the shadows produced by each pole be measured. All right. So he's going to take these poles that he's erected that are separated by a known distance as measured by paces. And at noon on the solstice, he wants to know the angle that the shadows from each pole have been cast. Okay. Here's why. Eratosthenes reckoned that the circumference of the earth could be calculated as a function of the distance between the 2 poles divided by the distance between the shadow angles measured as a fraction of 1 turn or 1 circle. Okay, so he's basically saying like, okay, these 2 poles are erected at a set distance around the planet Earth. And if I can measure the difference in the angles created between these shadows produced by these poles, and I know the distance between the poles, that will be able to tell me how big the circumference of the earth actually is. It's genius. Like this, he's doing this with a very rudimentary, at least rudimentary by our standards, understanding of, curves and circles and how to measure distances and all that sort of stuff. This is in 200 something BC. He gets the information. He sits down, he does his calculations, and at the end, he reckons by his calculation that the circumference of the earth is 252,000 stadia. Now, a single stadion is either equivalent to 155 or 160 meters. This is what the historians have calculated this out to be. There is a discrepancy there. There is a dispute. Some people say it's 155. Some people say it's 160. But either way, if you take the low end of a stadion measurement, he measures it to be 39,060 kilometers in circumference. Or if it's equivalent to 160 meters, then he reckons that the circumference of the earth is 40,320 kilometers. All right. The real measurement around the equator, if you wrap the tape measure around the equator, the earth is 40,075.017 kilometers in circumference. If you measure it from pole to pole, because remember the earth isn't a perfect sphere, it's 40,007.863 kilometers from pole to pole. In other words, he got it right. He measured it somewhere between 39,000 and 40,000, and the exact distance is 40,000 kilometers. He got this right by measuring shadows that were separated by a distance that was measured in people's steps. And he got the circumference of the earth right in like 250 something BC. That is crazy. He measured it to within 1% to 3% of the actual distance. But he's not done, because the next contribution he's going to have is to our understanding of geography. So the next thing he does is he makes a map of the entire world. All right. He used all the information at his disposal in the Great Library, and he made a map. He published this in a work entitled Geographica, but he sketches the entire known world. He labels them into 5 climate zones, 2 freezing ones around the poles, 2 temperate zones, and then an equatorial zone. He also plants the names and locations of over 400 cities on that map. So he's now created essentially the first atlas of the known world, or just at least the most recent and most accurate one and the most detailed one. Okay. He then overlays a grid of vertical and horizontal lines. Now, these are similar to longitude and latitude. These are not the same, but he comes up with the first way of measuring distances between cities using these lines. Why? Because he now knows the Earth's circumference. So he knows if they're this far apart, this is how many miles it translates to on the map. It was possible to calculate the actual distance between these cities, between different points on his map. And Geographica is also the first recorded instance of many geographical terms in use today, including the word geography. So the word geography comes from his book, Geographica, where he puts this map of the world in there and overlays so you're seeing, he just compiles knowledge. He used his intelligence to determine how big the Earth was. Then he says, okay, now I need to plot the known world on that map. And then because I know how big the Earth is, I can tell you exactly how far away these places are, which is crazy because we're still in the 3rd century BC at this point. Now, it should be obvious to you that Eratosthenes is really good at math, and he is. So he has a couple contributions to mathematics. One of them is the creation of something called the sieve of Eratosthenes. This is a way of identifying prime numbers. What's interesting is that he is able to, these sieves for finding prime numbers were things that ancient mathematicians love to come up with. So he's not the only person that does this, but he comes up with a really neat one of his own. And this is a way of identifying any prime number between any set number. So pick, a number here, a number there, and this will allow you to identify the prime numbers in between. It's kind of neat. He also provided a unique solution to a mathematical problem known as doubling the cube. So another thing you might need to know about mathematicians, they love to create problems for each other. So they try to find a way of saying, here's an interesting mathematical problem that I don't know how to solve. I'm putting this out there to the mathematical world. Try to find a way of solving this. And then once it's been solved, people are like, congratulations, you solved it. But then other people are going to try to find new and interesting ways of solving that problem, new elegant ways. And this is kind of the way new math gets developed, trying to tackle these problems. This mathematical problem is known as doubling the cube. It's also known as the Delian problem. And he actually came up with a way of doing this mechanically through the production of something called a mesolabio. This is really interesting. So the problem with doubling the cube goes as follows. If you have a side of a cube, let's say the distance is x, okay? What do you need to do to increase the length of one edge of that cube so that the volume of the cube doubles? Okay. And this seems easy, right? Oh, okay. Well, I want to, so I've got this side labeled X. That's the distance. I want to make a cube that has double the volume. How long does each edge have to be? And you're tempted to say, oh, we'll just double the length of each side. You can't do that, right? Because doubling the length of a side, when you do volume, it's a cube root. It's a cubic problem. It's one edge times one edge times one edge because you need the length, the width, and the depth. So if you double the lengths, you actually increase the volume by more than double because it's a cubic function. So this actually becomes really, really tricky. And the bigger problem that it comes down to is you end up having to multiply by the cube root of 2, which is really challenging. And it turns out that you can't actually do this with a compass and a straight edge. This is how people tried to do it. And it's actually been mathematically proven that now that you can't do that, but it took about 1,000 years to get to that point. There were solutions to this problem before that, but he comes up with this mesolabio, which is it's essentially 3 identical triangles next to each other, and then there are parallel bars and these strings on there. And as you slide it, it kind of tells you Like if your original side is this length, then it needs to be this length for the cube to double. I don't really need to get too much into it. He ends up solving this problem, and then to like celebrate his accomplishment, he creates a bronze version of this device, and then he gives it to King Ptolemy III. Is like, here, look how intelligent we are. So it's not huge that you understand the delium problem, but understand that he was an accomplished mathematician. He had really interesting ways of solving mathematical problems. And you can see a little bit of like Archimedes in that, right? Like he comes up with a mechanical device to solve a mathematical problem. So it shouldn't shock you that like he and Archimedes are friends, right? Archimedes used certain mechanical ways of solving his problems, and Eratosthenes develops a mechanical way of solving a problem that he's interested in. Eratosthenes also did some other cool things. He attempted to calculate the distance between the Earth and the Sun, as well as the approximate size of the Sun. So first off, he calculates that the Sun is 27 times larger than Earth. It's actually 109 times the size of Earth. But depending on how you interpret his calculations, he actually may have gotten the distance to the Sun and the Earth pretty accurately. A lot of what we understand about this is from the work of Eusebius of Caesarea, which was written in the 4th century, so like 600 years later. But if it's translated properly, it turns out that Eratosthenes measured the distance between the Earth and the Sun to be about 149 million kilometers, which it is. So he actually got it right, maybe. Like if Eusebius of Caesarea's work is translated correctly, then he actually nailed it, which is pretty freaking impressive. So it turns out if he can measure distance, he's pretty good. Size, not great at. He also gave us the leap year. So he correctly predicted what's called the ecliptic of Earth, which is the planar path around the sun. And because of the nature of this path, he predicted that in every 4th year, there'd be 366 days. So he correctly predicted how long a year is based on the distance around the sun, which is really, really cool. Just like Archimedes and Euclid before him, there are a few modern things named in his honor. He has a lunar crater. There is a geological structure in the Mediterranean Sea named after him, and a point in the Shetland Islands of Antarctica named in his honor. So that's Eratosthenes. The next scholar we're going to move on to is a man named Apollonius of Perga. I will label him as the original conehead. So if you're not a Xennial like me, I need to tell you what a conehead is. So you probably still know Saturday Night Live. It actually used to be funny. Back in the late 70s, early 80s, like when it first began, there was an actor on whose name is Dan Aykroyd. You probably heard of him. There was another woman named Jane Curtin. They were on the show, and they had a bit called the Coneheads, and they were like a recurring family of aliens that had moved to Earth, but their defining characteristic was they had these giant cone-shaped heads. They were completely bald, and they were very, very strange. Flash forward to the early 90s, and it becomes a movie, just like Saturday Night Live still does. Anything that's even remotely funny, they feel they need to turn into a movie series. This one was actually pretty good. It's a pretty classic 90s movie, but the most notable thing about this movie is the song Soul to Squeeze, which in my opinion is the Red Hot Chili Peppers' best song. And that was on this soundtrack. So it actually did have a pretty killer soundtrack. The movie's not bad. It's pretty good. If you want to know what 90s movies are like, this is a great one. And you might find yourself calling your parents parental units after having watched that. I still say it from time to time, weirdly. So there's a little bit of Xennial trivia for you. So anyways, Apollonius we're going to call the original conehead. And the main reason why is because he was interested in conics and conic sections. So Apollonius of Perga, as you would expect, was from the city of Perga, which was a Greek city in Anatolia, which is Turkey, we think. And although all the limited biographical data we have about him indicates that he was born in Perga, everything we know about his life and his work occurred in Alexandria. So again, we're back in Alexandria, and I'm hoping now you understand why I took some time to tell you about the city of Alexandria. It is believed that he was born in 240 BC and died around 190. But like so many of his contemporaries, the details of his life are somewhat foggy. Apollonius is best known for his work on conics, which I just mentioned, which was published in his only surviving work, which was aptly named Conics. Now, when we think about conics, you're thinking about something in the shape of those cardboard party hats. But Apollonius wasn't really concerned with the cone itself. He was more interested in what happens when you take a thin slice out of that party hat. We call these conic sections. So these include circles, ellipses, which are just stretched circles, parabolas, and hyperbolas, okay? Each of these, and it might be worthwhile for you to just hop online and look up conic sections. If you take one of these cones, and depending on how you take a slice out of that cone, you get one of these four things, these four sections, okay? Now, what's really interesting is Apollonius was the first person to define all of these curves as belonging to sections of a cone. Prior to Apollonius, all of these were treated as unique and distinct curves. Apollonius recognizes that, hey, these are actually all just sections of a cone, tying them all together in sort of a united field. And to this day, 2,000 years later, we still refer to them as conic sections. His work in conics is presented in the style of Euclid. So first, he's going to provide definitions and figures, and then he's going to have a series of propositions to be proven or to be proved using these definitions. So these propositions that he starts with include, or that he goes to solve, he includes the mathematical definitions of a circle, an ellipse, a parabola, and a hyperbola, which is good because that's what he's going to talk about. His proofs then examined numerous geometric properties of these conic sections, and he also was able to demonstrate their usefulness in developing solutions to other mathematical problems. In conics, we see the first use of the terms axis, diameter, and vertex, which are still in use today. And his study of relationships between geometric objects and the use of coordinate systems in geometry. So he gives us an actual coordinate system. We're not quite at the level of talking about our Cartesian geometry at this point, or Cartesian coordinates, but he's providing some sort of framework to help us understand where we are kind of in this system that he's developing. So this actually does become the precursor to analytical geometry, which would be done in the 17th century through the work of René Descartes and Pierre de Fermat. Okay, so he's literally, almost 2,000 years ahead of himself as he's describing these things and using a coordinate system to help people understand where he is. He then went on to use the principles he established in conics to solve problems in the field of optics and astronomy. So he starts this work in his conic sections, but then what he does is he goes in and says, okay, because I understand these concepts, I can now apply this to the real world. And what we see with Apollonius is a very modern approach to coupling theoretical science to empirical science. And it's very, very interesting, as you'll see here. So in astronomy, Apollonius was working under a geocentric model of the universe. Okay. And what we mean by that is he is of the belief that the Earth is the center of the universe, as were most people at that time. He also used geometric models to explain the movement of planets. So he views the Earth in the center, and then he says, I understand these conic sections. How can this help me understand the orbits and the movement of planets and stars in the night sky? Now, he used circular orbits, which we know actually aren't common. Most orbits are elliptical, but he's onto something. He's beginning to understand how these things move around each other. He also made an attempt to explain what some of the more irregular movements of some celestial bodies. One of which was which is referred to as apparent retrograde motion. So let me describe what this is. Retrograde motion is the apparent movement of an object in the direction opposite to that of other bodies part of the same system. What he didn't know, and when you see this type of motion, what you're actually observing is an illusion that's dependent on your perspective. Okay? So let me give you an example of this so you can understand what I'm trying to tell you. If you're looking at the night sky, it will appear that everything in the night sky is moving in one direction. Now, we know this is due to the rotation of the Earth. He doesn't know this at the time. But what happens from time to time is it actually appears that some of these celestial bodies, everything's moving in one direction, but occasionally it looks like a planet, a star, something isn't actually moving in the right direction. It's moving backwards relative to everything else. This is what retrograde motion is, movement against the current. We now know that this is an illusion, and it's based on perspective. And this can happen to us, and it does happen on a regular basis. We're all subject to this. Let me give you an example. If you look at the night sky and you see the moon, it will appear that the moon, just like the sun, moves from east to west in the night sky. So the sun in the morning rises in the east, sets in the west. To us, it appears that the moon does the exact same thing. So you would then assume that that the moon orbits the Earth from east to west. It actually doesn't. The moon orbits us from west to east, as do almost all man-made satellites. But because the Earth's rotation is faster than the moon's orbit around the Earth, it appears that the moon is rotating in the opposite direction. We're spinning too fast, and from our perspective, because we're moving in one direction, the moon's moving in another. It's almost like that illusion you get when you're at a stoplight and the car next to you starts moving, and you're like, "Oh my God, I'm moving backwards." You're not moving backwards. You're not moving at all. They're moving forwards, and their relative motion is giving you the appearance that you're moving in a backwards direction. So he actually tries to explain these aberrant movements in the night sky by coming up with the concept of eccentric orbits, or what are called epicycles. So that would be the circular motion around the edge of a circular orbit. So it's moving in a circle while it's moving in a circle around something else. Think of yourself in like one of the teacups at the county fair. You're spinning while you're also all spinning, that kind of thing. And again, you can observe some of these apparent retrograde motions while on the teacups, if you can keep your eyes open without getting dizzy. You will see people that are apparently moving in a direction that they're not moving because they're moving relative to you. So what I'm trying to get at here is, while we now know that his explanations, things like epicycles and eccentric orbits, are incorrect, the fact that he dedicated so much time to studying these and sharing his thoughts on these, his work from conic sections and all this sort of stuff, without this, we don't get the discoveries in the modern era, or even in like the Middle Ages or the Renaissance or anything like that, without his work. So Johannes Kepler comes along in the 16th century. He discovers elliptical orbits, and this helps to explain a lot of things about this retrograde motion. It helps us understand that it's not real. These eccentric orbits, these epicycles aren't real. But without the work of Apollonius, we don't even have that thinking for Johannes Kepler to go down that road, right? So that's what I'm trying to explain to you. And he also experimented with optics. He investigated the reflective properties of parabolic mirrors, which is an important sort of concept that applies to the modern field of optics. Now, Apollonius of Perga's work, his impact is still felt today. His insight into the mathematics of conical sections helped us develop modern geometry. His work in astronomy and optics quite literally changed how we view and understand our universe. As a side note, he has a crater on the moon named after him, and that would be a pretty cool thing for him to mention at parties if he wasn't super dead. So he does have at least that going for him. So the final thinker that we're going to talk about in this episode is Hipparchus, who I'm labeling as the Star Child. And you'll see why I've chosen that name for him after we've gone through his work. So Hipparchus was born around 190 BC in the city of Nicaea, which is near the central northern border of modern-day Turkey. It is believed that he died in the Greek city of Rhodes around 120 BC. Rhodes was actually the home to another one of the great wonders of the ancient world, the Colossus, which was supposed to be this giant bronze statue that stood at the entrance to the harbor of Rhodes. Now, if these dates are correct, this means he was born in the same year that Apollonius of Perga is supposed to have died. And because he's the last of these great thinkers, chronologically, he also benefits from the fact that all of these other great mathematicians had lived before him, and he had their work at his disposal as he developed his own mathematical treatises. And what Hipparchus is going to do with this knowledge is actually develop the mathematical field of trigonometry. So in addition to his mathematical contributions, he is also regarded by some as the greatest of the ancient astronomers, and possibly one of the greatest astronomers in history. So let's start with his math, and then we'll end with the stars. So trigonometry. Hipparchus was very interested in studying the relationship between angles and distances within a circle. So he actually was the person that established the convention of dividing a circle into 360 degrees. He took a circle, and one of the things you have to understand is he uses a mathematical system based on 60, not based on 10. So 360 degrees is just 6 times around, okay? He also developed the first trigonometric tables by measuring chord length within a circle of a defined size. So this would be the analogous to modern day sine values. So you can get these things called sine tables. And if you're talking about a chord, the easiest way I can describe it to you is this. Imagine a pie, okay? And at the exact center of that pie, like the exact mathematical center of that circular pie, there's a point, okay? Now what you're going to do is you are going to take 2 lines, and you're going to cut a piece of that pie. So you're going to take a straight line and measure from the center of that out to the circumference, the edge, the crust of the pie. And then you're going to measure the same distance. You're going to make another pie piece going out, or another cut going out to create the pie piece, right? So now you've got that center point and then 2 straight lines that are going out towards the edge of the pie, and that's going to make your pie piece. That's the size of the piece you want. Chord length would be if you take the points where the 2 lines cut the crust, and then draw a line to connect them. You're not following the curvature, right? You're not following the curvature of the pie crust. It's a straight line connecting those. That's the chord. So he developed tables by saying, like, if you know how big the circle is, so how long those lines have to be, those cuts have to be, and you know the angle between those lines, this table will give you the size of that line between those. This is actually a huge advance in mathematics, because using these, Greek mathematicians were now able to develop quantitative and predictive astronomical models. Like, instead of having to do all these measurements, they just have to say, okay, if I know the distance here, and I know the angle, then I know the distance between these points. This is pretty massive in terms of the world of astronomy. It also helped him, as well as other Greek mathematicians, solve several problems in the world of spherical geometry that were pretty much unsolvable up to that point. So what's going to happen is just this ability to sort of make these measurements are going to be useful in his astronomical studies, but would also be further developed by future mathematicians and then eventually become the mature field of modern trigonometry. So he lays the groundwork for this just in his work. It's also said using these methods, he actually outdid Archimedes to develop a better approximation of pi. So again, pi, right? We're now at the stage of, well, how accurate can we detect pi? That's where Hipparchus is headed here. So let's talk about how he takes his mathematical work and applies it to astronomy. So as I said, he's regarded as one of the greatest astronomers in history. And one of the things that he did very, very well was catalog the night sky. He was incredibly careful about annotating where everything in the night sky was. And through his observations, he created a catalog of 850 stars, as well as their position in the night sky. And he mapped them onto a coordinate system that he developed. He even categorized them according to their relative brightness. So this guy spent a lot of time. This guy must have worked at night. Like, this guy must have slept all day and just been up all night categorizing where in the sky these stars happen to be. And he builds these star maps, and then he eventually turns star maps into star globes. So these celestial globes that he creates are essentially a sphere modeling the Earth, and then a spherical map of the stars and constellations fitted over this. And using this, because he figured this out, he was able to predict the movement of the stars across the night sky. Like he could tell you exactly where the stars would be in the night sky whenever you wanted to. Now, for those of you who have a little bit of knowledge of ancient history, or if you've watched the History Channel and listened to some of these wackadoo sort of ancient aliens scholars, you might be familiar with something called the Antikythera mechanism. Okay, so the Antikythera mechanism is this really intricate device that dates back to the 2nd century BC that was discovered. And when you look at it, it is highly complicated. It's a series of gears and all this sort of stuff. And what we now know is that the Antikythera mechanism is actually an ancient analog computer. And it was used to predict the positions of the stars in the sky, as well as when eclipses were going to occur decades in advance. So this is a pretty significant technological advancement. And it's also considered possible that Hipparchus's work or he himself were actually consulted in the building of this mechanism, because it was built in the right place and in the right time. And because it focuses so heavily on work that Hipparchus developed on his own, it's quite likely that whoever developed the Antikythera mechanism either consulted him or basically just went, oh, I'm going to use Hipparchus's work and develop this. So either way, it's more than likely, almost certain, that Hipparchus was either directly or indirectly responsible for the construction of this Antikythera mechanism, which is really, really cool. But one interesting observation that he made while he was developing his star catalog was that the position of some of the stars in the sky had actually shifted slightly compared to observations that had made by earlier astronomers. So like I said, he benefits from the fact that he comes along a little bit later in the game. There were other astronomers who had followed stars through the night sky and sort of measured where they had been. And based on their work, he goes, what I'm seeing is different than what they saw, slightly. He also makes measurements during comparing tropical years, the length of time that takes the Earth to orbit the sun, versus sidereal years, which is the length of time it takes the Earth to orbit the sun with respect to another star. These matter in astronomy. So is it literally like the calendar year? How long does it take the Earth to go around the sun? Or if you're measuring it based on the movement of the Earth around the sun, but based on the perspective of another star. And what he says is there are small discrepancies there. There's small discrepancies between how our position changes relative to another star versus the star that we orbit. Now, to you and me, that doesn't mean shit. Like I look at him and be like, that's interesting. He goes, no. He goes, the only way this works is if the Earth wobbles on its axis. Like the Earth isn't vertically straight up and down, that it wobbles a little bit like a top before it falls. And he concludes that, yeah, the Earth's axis has a wobble to it. He calls this the precession of the equinoxes. And he goes, okay, he's like, well, based on these discrepancies in the location of certain stars at certain times of the year and all that sort of stuff, I would guess that the equinoxes move at a rate of not less than 1 degree per century, which is ridiculously accurate because we now know that it's about 1 degree every 72 years. So like, again, just like we saw with Eratosthenes measuring, the circumference of the Earth to within like 1 to 3% by measuring the shadows that sticks make on during the summer solstice. This guy looks at, he doesn't, like, he's looking with his naked eye. He's measuring things with a coordinate system they came up with. And he's like, yeah, looks like the Earth wobbles a bit. It's at least 1 degree per century. Well, he's ridiculously close. It's just amazing what some of these ancient astronomers and mathematicians were able to do. It's crazy. They don't have the tools that we have, and they're able to figure these things out. He also developed these exquisite models for the apparent motion of the moon and the sun across the sky. So he's got like these really cool like devices and models that he's created to show this sort of stuff. He uses knowledge that had been possessed by generations of another group of people from Mesopotamia called the Chaldeans. So he goes, he learns their mathematics. Again, here's the influx, right? This is the influx of knowledge coming from Mesopotamia, which is modern day Iraq. This wouldn't have been part of the Greek sphere of influence if it wasn't for Alexander the Great. But now because this was Persian, now we're bringing this in and it's being incorporated into the knowledge of the Greeks. And he's able to more accurately define the eclipse period in terms of what we call synodic months, which is a measurement of full moon to full moon. And he uses trigonometry to refine Apollonius of Perga's model for the orbit of the moon. And then this information, coupled with observations of the sun's apparent motion, allowed him to make incredibly precise predictions about future eclipses. So he's taking all of this knowledge from all of these different places and saying like, yeah, well, if I take this information, put it all together, this tells me that this is when an eclipse is going to happen. He's also, as far as we know, the first person to say, hey, not everybody's going to see an eclipse at the same time, because we don't all share the same perspective with relation to the moon and the sun. So we could see an eclipse here, but over here in this part of the world, they might not see it. That's we know that's absolutely the case. Go look at those eclipse maps and you can see where people are trying to, they're trying to stay on that line so they can see the eclipse perfectly. And that if you're off this line, you might not see the full blocking and it might be a partial eclipse. And in other parts of the world, there's no eclipse at all. Hipparchus is describing this and he knows this is true because of the mathematics, because of his observations, and because he's incorporated knowledge from people thousands of miles away from where he exists. He also examined the motion of the sun. During his life, he made 20 solstice observations, which is determining the exact time of the solstice. Coupling this with observations made about the timing of the equinoxes, he then calculates that spring, as measured in the length of time from the spring equinox to the summer solstice, was longer than the summer, as measured from the summer solstice to the fall equinox by 2 days. He realizes that there's a gap between these, that essentially spring is longer than the summer. It's 94 and a half days versus 92 and a half days. And he goes, well, that doesn't make sense. If there was a truly circular orbit, all of the distances would be even. And then what you would expect him to say is, well, that must mean that the Earth orbits the sun on an ellipse, but he doesn't. He just argues that the Earth was slightly off center with respect to the sun's orbit. Remember, geocentric. He's viewing the Earth as the sun is going around the Earth. When we get to Kepler and we have the heliocentric model of the universe, Kepler goes, oh, this is more easily explained by an elliptical orbit of the Earth around the sun. It just took a few thousand years to get there. But again, his observations track with what we know is actual reality. It's just his explanations are slightly off. But when you realize he's viewing the Earth as being the center of the universe and everything revolving around it, his explanations actually make sense. It's only when you get a different perspective, you get new knowledge, then you can say, oh, I agree with his observation. I have a better explanation for it. That is how science is designed to work. Hipparchus also attempted to measure the distance between the Earth and the Moon and the Earth and the Sun, as well as the sizes of both. He calculated the distance between the Sun and the Earth to be about 2,500 Earth radii, which is a little over 16 million kilometers. As noted before, it's actually 149 million kilometers. So point for Eratosthenes on this. And for the Moon, he measured it to be 60 and a half Earth radii, which is 385,000 kilometers, which is actually pretty damn close. The real value is somewhere between 363,000 and 407,000 kilometers. Remember, there's an elliptical orbit there, so it depends on where it is in its orbit, but 385,000 is smack in the middle of those two, so damn good job there from Hipparchus. Theon of Smyrna also wrote that according to Hipparchus, the sun is 1,880 times the size of Earth if measured by volume. It's not. It's 1.3 million times. He also reckoned that the Earth was 27 times the size of the Moon. It's not. It's actually 49 times if we're using the volume of these bodies as the measuring tool. In terms of geography, Hipparchus built off of Eratosthenes' grids. Hipparchus used a grade system based on the position of the stars to determine latitude rather than relying on the sun's location alone. This is actually more accurate because you're tethering it to two things. He also hypothesized a method for establishing longitudinal distances based on the observation of eclipses from different locations. He didn't do it, but he said this is something that we could do. And this is an ancient debate that we no longer have, but he also argued strongly against the belief that the Caspian Sea, the Atlantic Ocean, and the Indian Ocean were all one body of water. Now, depending on how you view this, one way or the other, because, it is true that the Atlantic and the Indian Ocean do border each other, and then there's a whole argument about when one becomes the other. But he weighed in at least. Hipparchus was brilliant. His mathematical work served as a foundation for future mathematicians and still lives on to this day, right? He gives us trigonometry. Sorry that happened to us. But because of the math that he developed and because of his astronomical discoveries and methodologies, he transformed our understanding of the universe and he influenced astronomers for centuries. Remember, he's held up as one of the greatest astronomers in history. He's doing this without many of the tools that future astronomers would have, and he makes remarkably accurate observations and calculations based on his observations. His work was so durable that much of it still remains relevant even after the Copernican revolution in the acceptance of the heliocentric model of the solar system. Again, the only thing that was really wrong about his work was he had the wrong perspective. He's using a geocentric model of the universe, which is why some of the things look confounding. Once you have better information and realize that the Earth is just one body rotating around several others, all of these other observations start to make sense and we can understand them from a better perspective. But it doesn't mean his observation is wrong. But perhaps his greatest legacy was Hipparchus's marriage of theoretical and observational science. He modeled this approach, this iterative approach of developing a theoretical model, using real-world observations to test that model, then refining his model based on that data, then getting new data to test that model. This is how modern science works, right? This is what we do. We come up with a hypothesis. We develop a model, right? Models are just fancy hypotheses. And then we say, okay, I'm going to test this. Does it hold up to real-world observations? Can I fit true data to these models, and does it hold up? If the answer is yes, I keep going. If the answer is no, I don't throw out the model. I go back to my classroom. I go back to my office. I go back to the laboratory. I refine my model to fit the new data. Then I test it again. Is it robust enough to survive this test of the data? Hipparchus does this, and he does it incredibly well, and that is why I believe, and most people believe, that his information, his data, his science still holds up almost 2,000 years later because he was using this iterative approach. This approach to investigating the natural world influences modern scientists from all fields, and it is now considered standard practice for scientific inquiry. Hipparchus has craters on the moon and Mars, as well as an asteroid named after him. He was also inducted into the International Space Hall of Fame in 2004. I'm sure his great, I'll just keep going, grandchildren would love to see him there. So that is the third and final individual I'm going to introduce you to in our podcast today. He is the fifth of the 5 scientists or mathematicians that I wanted to introduce you to in terms of the Hellenistic period. I hope you learned a lot. The Hellenistic period in Greece was an amazing period of mathematical progress and astronomical discovery. And we're going to see other periods like this again in other cultures and at other time points throughout our journey into scientific history. One thing that's going to come up repeatedly is how society influences scientific inquiry. That's something that we're going to talk a lot about. And that's one of the reasons why some of these stories are so interesting, right? The fact that some of these scientists had to overcome the societal standards, the beliefs from the society in which they came up. They have to overcome these biases. They have to overcome, this ignorance, or they have to understand how to navigate sort of these cultural periods of time. But the opposite is also true. There are periods of time where societies are open-minded, where there is peace, where there's an influx of ideas from other cultures and the free exchange from ideas from both within and without. And the Hellenistic period serves as a great model for this. It shows you what happens in a time of relative peace. It shows you what can happen when cultural and societal constraints don't restrict the flow of ideas. Don't restrict the expression of new thoughts, and allow thinkers to explore new, controversial, and exciting ideas. The Hellenistic period would come to an end with the suicide of Cleopatra in 30 BC. And after that, the future would be Roman, and it would be Romans carrying forward the torch of science into the next age. And that's what we're going to start talking about in my next episode. We're going to start talking about what life was like in Rome and how the Romans took a different approach to their understanding of science and its usefulness to their civilization. So I hope you'll stay tuned for that. I'll have that episode out to you shortly. Thank you so much for your attention. Again, I apologize for this podcast being a little bit late. If you're listening to this several years down the road, well, you're fine. Just go to the next episode. You didn't have to wait an extra couple of days. But for those of you who are listening in real time, I do apologize for that, and I'll try to stay on track whenever possible. Thank you so much for listening to these. I hope you're learning a lot. I hope you're enjoying them. I'm having fun making them for you. If you have any comments, concerns, feel free to post them on my YouTube page, That Biodoc on YouTube. You can also email me at thatbiodoc@gmail.com. I'd love to hear your thoughts. I love to hear your ideas. I love to hear what you're enjoying about the show or maybe what you're not. And again, I just appreciate you taking the time to listen in. Thank you so much, and I will talk to you soon. Bye.